Good day. So, in the last lecture we have looked at ATM technology in the box, in the sense that how it handles cells, how it makes cells, etc., etc. Today in the first half of this lecture, or first part of this lecture, we will discuss ATM signaling and routing. And since Ethernet networks and other kinds of networks are ubiquitous everywhere, so if ATM is used in a backbone, then how they would interoperate, that means an IP network and an ATM network. We will talk about that in the second part of this lecture. So, today we talk about ATM signaling, routing and LAN emulation. Okay. Now, in this, the first concept, if you remember, is that ATM uses virtual circuits. Okay. That means, so there are two ways to use packets: carry entire destination address in header, or carry only an identifier, also known as a labels. And labels have local significance, addresses have global significance. And signaling protocol fundamentally maps global addresses or paths or sequence of addresses to local labels. Now, what are we talking about? You remember that we just discussed this a little bit. We will go into this in much more detail when we discuss routing of IP packets, which we will take up after this lecture. Now, usually when you have a packet switch network, then each packet is considered in one extreme, that is in the IPN. Each packet is considered on its own. That means each packet must contain the destination address at the very least. It also contains the source address, that is different. So, it must contain the destination address, so that looking at each packet an intermediate router would know where it should go. So, that is one end of the spectrum, whereas in the connection oriented system we know that a physical connection is set up. Now, in ATM what we do is that we set up virtual circuits or virtual paths, alright. Now, in virtual circuits or virtual paths, what happens is that these cells, and you remember these ATM cells are very small, okay, only 53 bytes long. So, each of the cell will contain some local label, alright. So, a path is set up. Now, setting up a path in ATM means that each of the intermediate switches would know that a flow of cells is going to go through them from one source to some source to some destination, alright. So, they make provision for this to accommodate this flow. So, they make provision for a virtual circuit. And then once they do that, once they set up this virtual circuit in the starting phase, and we will come to how that is set up. After that, each of the cells need not contain any specific identifier or specific address for the destination. It just needs a small address which is the which sort of tells the intermediate switches which virtual circuit to use. So, it contains a virtual circuit identifier. Actually, it is divided into two parts, as we have seen in the cell header. We have the VPI part and the VCI part. So, simply looking at that label, the intermediate switch would know that which virtual circuit to use. Okay. Now, but before this virtual circuit, so as we see that we have in the sample, suppose we have the data. Now, in the ATM cell, the data would be preceded by simply by the virtual circuit identifier, and this might have two parts, VPI and VCI. Whereas in a regular datagram, the entire address may have to be there in each packet. Okay. Now, in VPI VCI assignment and use, now in this case all packets must follow the same path, unlike a datagram. Okay. Why is that so? Because this virtual circuit is set up before any actual flow of packets begin. So, there is a time for this circuit setup and this circuit is not a physical circuit like we have in a maybe in a telephone network, but this is a virtual circuit. That means each of the intermediate nodes simply know that flow is about to begin. So, this has to be set up. Now, once this is set up, all packets would flow through the same path, or that means all these cells would flow through the same path. Switches store per VCI state, for example QoS, quality of service information about this particular VCI and so on. Now, signaling, this implies separation of data and control. So when we do ATM signaling, we are talking about setting up the entire path. We will come to that. Small IDs can be looked up, that means exact much quickly in hardware. So that is one good thing. If you have a small VCI, that means virtual circuit identifier, that can be looked up very quickly in a hardware. So this is a sort of bottleneck in a router. So this can be handled very fast. Harder to do this with IP address, that means this longest prefix match, we will come to that later on. Setup must precede data transfer. So this is the other cons of this using VPI and VCI. We must set up, that means delay short messages. There are two types of virtual circuits, switched and permanent virtual circuits. All right. So this is an example. So the switch knows in the input ports say 1 and 2, say 137, if these are the VPI or VCI identifier, then out will be through port 3 135. All right. Similarly 334 and similarly port 1 and for 34. So it will go to 4256 and so on. So there is a table which simply quickly matches the VPI VCI value and puts it on another VCI VPI pair on the other side. So this is how VPI VCIs are assigned and used. Now we come to ATM addresses. This address that I am going to talk about is then now different from the VPI VCI, that is the virtual circuit identifier, virtual path identifier, which is simply local. But before, for setting up the path initially, you require an address, and here you do not require, I mean you cannot do with a local address, you have to do with a globally consistent address. All right. And this global address of ATM is 20 bytes long. So there is a 20 byte long ATM address which you use for setting up circuit. As mentioned previously, that there are two types of circuits, switched virtual circuits and permanent virtual circuits. In permanent virtual circuits, what happens is that a path is set up initially maybe by manually. All right. So manually the path is set up and the path remains. So that is a permanent virtual circuit. So that whenever so that if you know that there are two endpoints between which a lot of traffic will flow, you may sort of skip this overhead of path setup and set up a permanent virtual circuit. This is like a lease line. All right. So whenever there is something to go from this source to that destination, it will simply use the pre-existing permanent virtual circuit. Or otherwise we may have a switched virtual circuit, that means this virtual circuit is set up on the fly as the network is being used. So and in a ATM switch hundreds of thousands or maybe millions of virtual circuits may be set up or taken down every second. All right. So this is a very fast process. Anyway, for setting up this virtual circuit we require an ATM format, and this is a 20 byte long address. Okay. Unlike an IP address which is only 4 bytes, this is 20 bytes. So this is a very, very long address. This is left to right hierarchical. Okay. There are so this level 1, level 2, level 3 and level 4 are there. The first two levels they have a 13 byte prefix. So this is the levels of hierarchy, and then this part is usually used for the actual network addressing inside. And there are various schemes. So since this has got such a long address, this can accommodate various schemes. So what the people who designed ATM, what they did was that this was sort of, as I mentioned, that this was conceived as a technology which will subsume and absorb all pre-existing technologies. Okay. So, they tried to accommodate all different kinds of addressing scheme in one super addressing scheme, which is this ATM addressing scheme. So, if as you will see here, so this is, there are different types of addresses are possible, and it is possible, since there are 20 bytes, it is possible to have more number of schemes, but right now these are the schemes. This 1 byte plus 2 byte 3 plus 10 13. So, up to this is supplied by the network, and this 6 bytes, this is end system supplied, and this is not used in routing, this is used maybe inside the host, this may be used, this 1 byte for something, for maybe demultiplexing inside anyway. And this network supplied part, okay, there are first of all we have one 1 byte which is indicate that what is the scheme. This basically indicates the scheme. Right now 3 NSAP like, that NSAP is network service access point address formats, DCC, ICD and E164. So, there could be E164 number or ICD number or DCC number. So, this is a data country code which uses 2 bytes and 10 bytes are used for the other part of the network. So, actually I will tell you here, authority and format identifier, first thing. So, 39 means this is ISO DCC. 47 is British Standards Institute ICT, and 45 is ITU ISDN, which means that this E164 that you see, this is actually an ISDN number, alright. ISDN uses 15 characters, so that is 15 binary coded decimals, so that is 7.5 bytes. So, this entire ISDN number which again can subsume telephone numbers. So, this entire ISDN number can be put over here, alright. So, you could do that. So, that is that E164, ISDN uses E164 numbers. ATM forum extended E164 addresses to NSAP format, and E164 numbers is filled with leading zeros to make 15 digits, that is F16 is padded to make 8 bytes instead of 7.5 bytes. Okay. So, end system identifier, this is the other part, you see this is the end system identifier part, this 6 bytes, and this 6 bytes could be various things. Specifically this 6 byte could be 48 bit IEEE MAC address. You remember the MAC address that we use in the data link layer, that is a 6 byte supplied by IEEE. So, that entire 6 byte can straightaway be incorporated in the low order bits of the address. Selector is for use inside the host, and all ATM addresses are just 20 bytes long. Okay. So, there are various ways you can route this ATM given an ATM address. So, there are various schemes are possible. ATM addresses, so since various schemes are possible, ATM addresses could be of variable lengths and have an initial domain part and a domain specific part. The initial domain part consists of 2 fields, as we have already mentioned, AFI, that is the authority and format indicator, okay, and IDI, there is an initial domain identifier. This identifies the domain within the purview of a given addressing authority. Okay. Okay, I do not think alright. In a particular format, say ICD, International Code Designator, all addresses have a unique fixed length prefix. Now, the high order DSP are the high order bits of domain specific parts and roughly correspond to the low order part of the network number in IP. ESI is the second. So, we need not go into this, all I am trying to show is that this particular scheme can sort of subsume a lot of other schemes which were possible, and the reason I am showing this in this fashion is that a similar thing was tried later on in IP version 6. So, later on when we look at IP, we will see that the current version which is going on mostly is IP version 4, and people have already developed an IP version 6. There also we have got a very large address field where a lot of previous things had to be, I mean it was tried that a lot of previous schemes could be subsumed in this. One of the difficulties you remember of this IP addressing scheme was that it was done in a very haphazard manner. Unlike let us say your telephone numbers. For example, the telephone numbers, it is geographically distributed. That means you put a particular some few digits, first few digits, and that will immediately indicate which country and which region in which country and so on. Okay. So it is easy, very easy for the router to just look at I mean a router which is far away, it will just look at the first few digits and send it to the right trunk. So, but that is not possible in the IP version 4 which is used, where it is where it has got no geographic correlation. So, you have to keep a very long table and look into the table. We will look into that. So, once again, when people develop these ATM addresses or the IP version 6, okay, they try to bring back some order into this addressing scheme. Okay, then now for setting up connections, ATM supports both permanent virtual circuits and switched virtual circuits. PVCs are pre-coded in each switch along the way and are always present. They are like lease lines which do not need any connection setup. For connection setup, you have this there is an user network interface or UNI and the network interface which is the NNI. Okay. Then there is a part called Q.2931 which is an ITU protocol for setting up paths, and then this SSCOP, that means service specific connection oriented protocol, and of course you have the AL and ATM, these layers. We have already talked about these two layers earlier. So unfortunately this whole scheme came out to be quite a complex one. So we will not go into all the details of this. We had already seen about the ATM layer and the AL layer which is in the user plane. Today we are going to talk a little bit on this control plane, which has one service AL and which has got three parts: SSCF, SSCOP and ALCP, AL common part. And then there is this for setting up the circuits etc. we have Q.2931, BISUP and PNNI. Okay. And this is public network to network interface. UNI is the user interface of ATM networks and consists of signaling protocol for setting up circuits of a certain quality and the format of the cells. The NNI deals with the issue of signaling and data transfer, as well as routing, data transfer, operations and management. All right. And if you remember that there is also a slight difference between the cells which you go through in the UNI part and the this NNI part. In the NNI part the GFC is dropped and we use the whole thing for to accommodate more number of virtual circuits. But anyway, that is a small technical point. So if you look at the control stack, that means control plane stack, we have this Q2931 sitting on this SSCF, this SAAL, that means service ATM adaptation layer, which again sits on ATM layer, which again sits on some physical layer. So there is a virtual link between ATM and ATM, ALCP and ALCP and so on, between, as usual, in a stack from the source to the destination or from one hop to the other. All right. Now let us see what is Q2931. We will obviously not go into this, as you can imagine that the once again the protocol is quite complex. We will just touch some aspects of it. This is an ITU protocol, is for setting up a connection. First it sends a request in the meta signaling channel 0 to negotiate a quality of service for a signaling channel. Okay. So this is a bit maybe well, what is done is that you have to set up a circuit. Now for setting up this circuit you have to do some communication. Now this communication again will be what? Again through ATM. All right. Now how is that done? It actually, for that also it will require some kind of virtual path and virtual circuit, and ATM is quite strong on quality of service. So there is a question of quality of service of the service channel also. Okay. Although the service channel would be used for very short time, I mean once the circuit is set up, that service channel may be released. All right. So there is a meta signaling channel called 0, where you can sort of negotiate the quality of service for the which signal channel with what quality of service. Okay. Otherwise there is a default which is that VP0 VC5. that means virtual path number 0, and in virtual path number 0, path, if you remember, is a bundle of circuits. So, in that virtual path number 0, you take the VC5, okay, which is a standard channel where you put your request for signaling, okay, request for this path setting up. Now, if this is successful, then a new VC is assigned for connection setup request and replies. Okay, then you first make the request in this channel, then a new VC would be assigned for this particular connection setup. So, the Q2931, if you remember, that is at the top of the control plane protocol stack, which sort of initiates the setting up of the circuit and sort of handles setting up of circuits. That is how it is done. Below the Q2931, we have the signaling L, alright, that means signaling ATM adaptation layer, which again contains of 3 parts. Service specific coordination function provides, this is the provides interface to Q2931, interface between Q2931 and the ATM stack. Service specific connection oriented protocol, which is that SSCOP, this is handles error and loss recovery. This we are all talking about the communication for setting up circuits, that means for communication for the control purpose, and AL common part which handles error detection. So, this is roughly the stack, and then there are various kinds of once again I am not going into the details of this, that in the forward direction and in the backward direction there are various parameters that you can specify for the quality of service. Okay. ATM when it was the first very serious attempts to handle the issue of quality of service, and now of course it has become so important that in the IP domain also which is coming out to be the dominant technology, there also quality of service has become important, and people have thought of various schemes for handling quality of service, and many of the schemes, if you look deeply into it, they are sort of what people had already thought about for the ATM, that has been adapted in various ways. Okay. So, anyway, the quality of service, so maybe later on we will talk in details about quality of service. Today we will just touch it. There are some various parameters like peak cell rate, that means what is the peak rate at which you will be pumping in cell, sustainable cell rate, maximum bus size, etc. So, all these the different parameters can be negotiated for one particular virtual circuit, and when a path is set up, along the way, as I mentioned, that each of the ATM switches on the way gets ready, that means sets up this path, that means it makes some provision for supporting that particular this new virtual circuit with that kind of service guarantee. Okay. If it cannot handle that, then maybe there will be some negotiation about it, that what can be handled and so on, alright. Leaky bucket is some kind of congestion control algorithm, we will discuss it later. So, ATM connection types are of various types. The most predominant one are the switched virtual circuit, for which where you set up a path and then take it down, or permanent virtual circuit which is pre-coded. There are other connection types also, for example, simple point to point connection, symmetric or asymmetric bandwidth connection, point to multi-point connection, data flow in one direction only, or data is replicated by the network. So, this is an example of a point to multi-point network. Okay. Now, what happens when you do a ATM connection setup? Well, you put up a setup signal. So, this maybe say this is the source and this is the destination, these are the intermediate switches. So, from the source there is a setup signal which goes to the intermediate switch, which sends back some kind of acknowledgement saying that the call proceeding, and sends the setup signal to the next hop, and then the setup signal to the next hop. Okay. And each of them, I mean, immediately they will send back some kind of acknowledgement, and then when the call is accepted, then a connect signal will start flowing in the other direction, and when it reaches the source, then a connect acknowledgement will flow, and each of them will give this connect acknowledgement for this connect signal, and now of course the circuit has been set up, or alternatively the destination may reject it also, then he just simply sends a release kind of signal. And on the other hand, when the circuit is that is for circuit setting up, and for taking down a circuit, the source will send a release, that means he has finished sending. So, he will send a release and release complete, release complete, and so on, it will go on, and then finally the destination will send a release all the way back. I mean, the release could be initiated by the sender, or the release could be initiated by the destination also. That means, if at some point of time destination thinks I have had enough. Okay. And then of course the connection gets terminated and release is completed. Now, what does PNNI come into picture? PNNI is that private network to network interface. That means, so over here between the end system and the switch, we have the UNI, and then we have the NNI, where in the PNNI is a private network to network interface, and this could be between two switches, this could be between two entire networks. All right, private network node interface is there, and private network to network interface is there. So, in the PNNI, it uses link state routing protocol for ATM networks. We will look into the details of link state routing when we deal with OSPF in the IP world, since IP is the more prevalent technology. So, we will discuss it in detail there when we do it. Here in very short, I can just tell you this, that each node will periodically broadcast the state of the links to which it is connected to all parts of the network. So, all the switches get some global picture about the status of the various links, so that they can run some algorithm locally in a centralized fashion and find out all possible paths, and this they are going to use for setting up the path later on. All right. An actual situation, the situation actually is a little more complex than what I have just said, because there is a hierarchy mechanism ensures that this protocol scales well for large worldwide ATM networks. Okay. A key feature of the PNNI hierarchy mechanism is its ability to automatically configure itself in networks in which the address structure reflects the topology. Okay, that is also there. Well, there are two things here. One is this hierarchy we are talking about, and the same kind of thing is used in OSPF, what is called in IP domain the OSPF. So, when we discuss OSPF, we will get into the details of this, but there is a hierarchy over there. You can imagine that if all, if all were ATM switches, which they are not, but suppose they were all, and that was the vision, and if all the ATM switches were communicating with everybody else with their link states, the database and everything would become huge, it would not scale at all. So, in order to scale to a very large network, what is done is done, it is done in a hierarchical fashion, meaning that you can have a hierarchy of networks, and at each hierarchy the peers run some kind of PNNI, all right, for routing within the hierarchy, within that level of hierarchy, and at a lower level they will again run maybe PNNI for that level, and various hierarchy levels are possible. You have seen that the ATM address is given in such a way that it is we have just shown you the broad boundaries, but within that boundary it can be further divided into a number of hierarchies, and this would again different designated authorities can break their own thing in different ways. So, all this flexibility are possible. Not only that, PNNI also allows that in some plane, in some hierarchy, one kind of addressing scheme is used, in another part another kind of addressing scheme is used, even that is possible. Okay, so anyway, the sum and substance is that it scales to very large networks, supports hierarchical routing, supports quality of service, supports multiple routing metrics and attributes, because when you broadcast the link state, that means the state of the link, you may also broadcast all different kinds of parameters about the links, that what is it that can be, how much can be handled in that on that link, or how much can be handled by the switch, etc. That can be propagated throughout the network. So that you have a fair idea about what is possible and what is not possible, and then you can plan your route in the source in a particular fashion. So use source routed connection setup. So the since the source has the global picture, it will use that global picture to compute the route and set up the connection using, and once it decides okay, this is the route that I should follow, then he will use the Q2931 to give all these connection setup, that setup request and that acknowledgement and release, etc., etc., that he will use. So operates in the presence of partitioned areas. So PNNI features, it provides dynamic routing, that means the link states that may change. So but from time to time each of the switches are going to broadcast their link states responsive to changes in source resource availability. Separates the routing protocol used within a peer group from that used among peer groups. All right. So as I said, that it's a various hierarchy as possible. Interoperates with external routing domains, okay, which are not necessarily using PNI, that is also possible, and supports both physical links and tunneling over virtual circuits. So this is an example of hierarchy. What I am saying is that this big network, which is again a network of networks, is represented maybe by one node in this level, in the top level of the hierarchy. Similarly here, similarly here, and here you use PNNI to sort of plan a route like this. Now within the network, you might have to again do a planning, and each node may again be corresponding to some more another network in a lower level. So at each higher level of the hierarchy, you can use PNNI to plan the route. So if there is an A.1.1, its view, now A.1.1 is something below this A.1 level. Now in this below A.1 level, that A.1.1, so far as that A.1, A.1.2, A.1.3, these are explicit. These have abstracted notions of A2, and then when you come to B, this is simply B and C. All right. Although when the call setup is passing through B, it may come all the way down over here and do the actual path setup, that may happen. So this way the hierarchy works, and once at any level of the hierarchy. So here there you will make a, rather A.1.1 will make a source route which goes through maybe A.1.2, A2, then B, then C. All right. So source specifies route as a list of all intermediate systems in the route. Okay, so this was the original idea also in the token ring. So for this, it uses a designated transit list DTL, which is in the form of a stack, as I will just show you. So source route across each level of hierarchy, entry switch of each peer group specifies complete route through that group, and set of details manipulation implemented as a stack. So as you say, and that AB may be in the bottom of the stack, this is at the top level of the hierarchy, then A12, then A11, A12. So this is how it is put in a stack and the path is computed. Okay, now just a few words about the quality of service parameters. I will just mention some of the metrics, etc. We will not go once again very deep into this because we don't have that much time, but it will give you some idea about what we mean when we say that quality of service. One such parameter is a maximum cell transfer delay. Okay, that means from the beginning of the first bit of the first cell to the last bit of the cell, what is the delay. maximum cell delay variation. So, what is the variation of this time MCTD? Maximum cell loss ratio, whether cells could be lost, and if so, what is the its maximum cell loss ratio, administrative weight, etc. Available cell rate, what is the how much capacity is available right now, cell rate margin is allocated minus actual, variation factor, branching flag, restricted transit flag. So, these are all different parameters and their attributes of QoS parameters and their attributes. Then one way this is handled is that generic call admission control. Now, generic call admission control is happens when you are on the source side, that means when you are deciding on the route and you are doing a source routing, remember. So, at that point whether you can admit a request which has come from the finally the you see the request must have come from the user. So, from the UNI etc., but at that particular point of time before making the request, because at the source when you are doing the routing, you know that this is the route which is possible and this is the maximum or best quality of service which he can allow. Okay. So, there is an admission control there which is a generic cell admission control run by a switch in choosing a source route, determines which path can probably support the call. So, that way it will try to sort of route the call, call setup. Actual call admission control, this is run by each switch. So, in the beginning we will run a GCSE as well as ACSE, and the intermediate switch will simply run an ACSE, which is the actual call admission control, that whether right now that the request has come to this switch, whether it can handle this request or not. So, this is the protocol which is running. Then there are traffic management functions. So, this call admission control is a kind of traffic management. Traffic shaping, that means limit burst length, space out cells etc., so that you get the maximum throughput. Usage parameter control, that means monitor and control traffic at the network entrance etc. So, various traffic management. So, both quality of service management as well as traffic management is possible in ATM, and there are extensive protocols for negotiating these various parameters and setting it up. Then there are selective cell discard, whether there is a cell loss thing called CLP or cell loss priority. If CLP is 1, that means these cells may be dropped if the situation so warrants. Okay. So, this is something like an unspecified bit rate, and it may have a very low priority and it may be dropped. Cells of non-compliant connections may be dropped and frame discarding etc. And then there is a feedback control, and feedback control, one example is an ABR scheme. We will just quickly look at a little bit of this. So, suppose so peak cell rate. So, I am not going into the details of these. Cell transfer delay, cell delay variation tolerance, cell loss ratio etc. These are the parameters. Explicit forward congestion indicator. Okay, so we will just I'll just have a quick look at ABR, which is a binary rate system, which sends an EFCI, which is an explicit forward congestion indicator, which is set to 0 at source, and congested switches set EFCI to 1. So, every NH cell destination sends an resource management cell to the source. So, what happens is that somewhere in between an intermediate source, this EFCI, this if it is congested, this may set it to 1, and then that information will flow back finally to the source, and the source may try to restrict its requests. So, sources send one RM cell every n cells. The RM cells contains the explicit rate that has been asked for. The destination returns the RM cell to the source. The switches adjust the rate down. Okay. That means it may, if it is congested, it may adjust the rate down. Source adjusts to the specified rate. So, whatever rate comes through this going up and coming down through this negotiation, that is what the source finally has to accept. Okay. Now, we will talk a little bit about LAN emulation, which is emulating a local area network when the backbone maybe is of an ATM, or when you use an ATM, but you still want to use Ethernet and IP, specifically IP in the nodes. And one very specific reason why this is required is that you see, one of the trouble why ATM was not successful in the LAN segment, although it was put as a LAN solution also in enterprise LAN solutions, but it did not succeed, was that there was hardly any software which was developed on ATM, okay, whereas a huge amount of software has been developed using IP, and so much of software has been developed in IP, you cannot throw it up, nor can you translate it to an ATM software overnight. So, that is very difficult. So, people took a more pragmatic approach and thought, okay, let the backbone network technology be that of ATM, or let us have an ATM, but let us emulate the LAN so that your software IP based software can still run. Okay. So, how that is done? So, problem: new networking software for ATM. Solution: let ATM network appear as a virtual LAN. Now, how can an ATM network appear as a virtual LAN? So, LAN emulation implemented as a device driver below the network layer. Okay. So, these are a LAN emulation bridge actually. So, if there is an ATM, so this will look like a LAN. Now, for this, one ATM LAN can be n virtual LANs. Many virtual LANs can be there in the same ATM LAN. I mean, if you look at just one of them, that is maybe sufficient. So, this is a logical subnets interconnected via routers. This is the this is what we want to sort of this is the abstraction, or this is the picture that we want to give to the world. So, need drivers in host to support each LAN. So, in actual practice only IEEE 802.3 and 5 were this thing supported, although FDDI can also be done. So, this is the picture. We have an ATM switch, we have some lane servers, maybe we have multiple LANs on this. So, we have a lane server for A and a lane server B. So, the logical view would be as if, and a router is also connected to the ATM switch. The logical view just looks like an IP network. We have a this A1, A2 connected via this network A, and B1, B2, and there is a network B which is connected, and these two networks, IP networks, are connected via router. This is the logical view, although the actual view is this. Now, how is this emulated here? So, it requires several components. So, one component is that we require a LAN emulation client in each host, all right. So, each host must have a LEC or LAN emulation client, which is a small software which can be sort of loaded in each host. LAN emulation configuration server, or LECS. Now, LECS will of course be a maybe in one central server will be taken as the LAN emulation configuration server. So, whenever somebody wants to join the LAN or leave the LAN, etc., it will, when it wants to join the LAN, it will get all the configuration parameters from this LECS. So, what the LAN emulation client will do is that LAN emulation client, the first thing it will do is that it will ask for the parameters from the LECS, all right. So, it has to know the address of the LECS, of course. And then there is a LAN emulation server itself, the LES, and a broadcast and unknown server. So, if there is this is something doing something like the broadcasting in a network which is done, we know that if in a particular network, says for ARP, we want to do an address resolution protocol. So, what we do is that we broadcast a request that this is the IP address, what is the data link address, all right. So, here now doing broadcast, you remember that this ATM works on this point to point essentially mostly as a point to point connection, all right, although point to multi point is possible, but not in both direction. Now, how do you broadcast? In that case, how do you broadcast? So, instead of trying to do the broadcast from the host itself, what it does is that each host, this LAN emulation client, what it will do is that if it has to broadcast anything, it will send it to another server called bus, okay, broadcast an unknown server, and the broadcast, and now this bus will there is a virtual connection between every host and the bus will send the broadcast to each of the hosts. So, that way in an indirect fashion the broadcast takes place. Similarly, there is an unknown server, that means I do not know the address of the server, like an ARP. Once again you send the request to this bus and bus will find out and finally give you the address. So, these are the main components of LAN, namely LEC, LECS, LES and bus. Now, what does LES does? The basic function of the LE server is to provide directory, multicast and address resolution services to the LE layers in the workstation. Okay. So, that is what the LAN emulation server does. It also provides a connectionless data transfer service to the LE layers in the workstation if needed. So, basically, and then by the way, who is the LE server? How do you know? For example, who is the bus server, where is the LE, etc., and how do you set up the connections, etc. So, these parameters will be known to the LECS, which will communicate to the LEC as the LEC joins the network. Initialization. So, the client gets address of LECS from its switch, uses well known LECS address or well known LECS PVC. So, there has to be a particular PVC which it starts using automatically. Client gets server's address from LECS. It also discovers its own ATM address if required for direct VCs. That means, if it wants to do some direct communication between two nodes, what is happening is that previously if it was Ethernet and IP, it would get the Ethernet address. So, here if it wants to do a direct communication, it has to get the ATM address of the other side if it wants to set up a direct VC instead of going via the servers. So, in that case it will require its own ATM address also, alright. Then it does a registration. Client sends a list of its MAC addresses to the server, declares whether it wants ARP request. So, these have to be known to the server, so that the server can give the service to other nodes connected to that network. Client sends ARP request to server. Suppose, how do you do address resolution? Client sends ARP request to server, unresolved request sent to client's bridges. Server's client's bridges answer the ARP, client sets up a direct connection. So, this is how a connection is set up. Now, broadcast stroke unknown server or bus, as I said, that it forwards multicast traffic to all members, and clients can also send unicast frames for unknown addresses. There are suppose some address is not known, so you send it to bus and then bus will try to find out. Okay. We are not going into all the details. There is a flush protocol. That means clients can send unicast packets via bus while trying to resolve the address. So, what might happen is that client may get try to get the address, then get some address, then maybe send it directly. What might happen is that something which was not sent directly and something which was sent directly, here the packets may come out of order. Okay. Remember, I mentioned this, that in ATM one guarantee is that that cells will not come out of order. Okay, cells may get lost, but cells will not come out of order, unlike pure datagram services. But in this particular case, this may happen because we are not talking about one particular VC. In one particular virtual circuit, packets will indeed not go out of order, but in this particular case it might. So, when direct VCC is set up, clients send a flush message to the destination. Destination returns it to source. Source can then send packets on busy. So, there is a flush message, so that this problem is solved. This is the flush protocol. There is another approach to this which is not using LAN, but uses classical IP over ATM. So, what is classical IP over ATM? The definitions for implementation of classical IP over ATM are described in RFC 1577. So, all the details are here. once again over here we will just simply mention it very quickly. This RFC considers only the application of a ATM as a direct replacement of the VARs, local LAN segments connecting IPN stations, which are the members, and routers operating in the classical LAN based paradigm. Issues raised by MAC level bridging and LAN emulation are not covered here. So, if you want to do classical IP over ATM, you have to do address resolution and encapsulation. These are the two issues to be considered here. Encapsulation consists of putting appropriate ATM header trailer to a packet, converting it to a number of cells and then sending them. So, this is encapsulation, which means that you have got an ATM packet. So, this is a classical IP running over ATM. You have got a big packet. Now, you know that in cells you have to break it up. So, you break it up and put a proper header on each and then send them. ATM features are not utilized and inter-network traffic handling is clunky. Okay, so each of the IP subnetwork is a logical IP subnetwork. So, all members of a logical IP subnetworks are able to communicate via ATM with all other members in the same LIS, which means that if two nodes are in the same logical IP subnetwork, that is same list, that means that you would set up a VC on this. So, there is a VC between every pair within amongst all nodes in a particular logical IP set marker. So, there is a VC mesh over there, alright. So, everybody can communicate to everybody else. Communication to hosts outside the list, local list, is provided via an IP router. This router is an ATM endpoint attached to the ATM network that is configured as a member of one or more lists. Naturally, just as a router have maybe a member of more than one network, similarly here the router is configured as a member of one or more lists. So, you have to do an address resolution. Suppose so the valid question over here is that if the IP address is this, what is the ATM address, alright. So, you have to do an ATM ARP. So, IP address to ATM address translation. So, address resolution protocol is used. Inverse ATM ARP, that means VC to IP address. Solution use ATM ARP server. So, there are ATM ARP servers over there. So, this is a diagram. Suppose this is a logical IP subnetwork number 1 and this is logical IP subnetwork number 2. Each of them have their ATM ARP server for doing your ARP, that means IP to ATM address translation and vice versa. Nodes are connected. Now, if A1 wants to communicate to B2, naturally at the A1 at the top level you give the IP address. Then it is sort of just previously we were breaking it up into data link address and we are going, and finally what is the route to take if it is in some other, if it is in the same list, of course you have a direct VC to it, alright. So, you have a direct virtual circuit, you will take that. If it is a different one, you will have to go through the router. So, each list has an ATM ARP server for resolution. Clients are configured with the server's ATM address and clients register at startup and periodically. In ATM ARP protocol is used to resolve a host's IP address for a known hardware address. So, it is the inverse ATM ARP. So, I have I mean of course, as you can understand, this ATM is a rather complex technology, and this is one of the reasons why it was not so successful, because it was complex, so it became very costly, alright. But as I said, that as you will find later on, that many of the ideas which were used in ATM, namely this about this quality of service, about setting up flows and setting up virtual circuits with VCI, VPI labels, these ideas were later on adopted in IP, and we will discuss it in one lecture called MPLS, that is multi-protocol label switching, where the similar ideas have been used to give this kind of services later on. And also ATM is also used even now quite extensively in big backbone networks because of the various facilities it has, although it is moved out of the LAN segment more or less these days, because the gigabit Ethernet has sort of replaced it simply because of cost. Thank you. Good day. So, today we will start our discussion on routing. Okay. Actually, we have already talked about routing a little bit in different contexts, specifically in the context of ATM, how the ATM virtual path etc. are set up. But today we will talk about the major area, we will start our discussion on the major area of routing, which is how and especially with reference to the TCP/IP stack, that is how packets are routed in an IP network. So, we will talk about today we start the introduction to routing, and then we will take up the discussion about different routing protocols in next set of lectures. Okay, so let us just recollect what is the job of the network layer, or what is routing. This is to carry data end to end, that is from the source to destination, perhaps through a number of intermediate subnets. Now, depending on whether connection oriented or connectionless services are used, other functionalities may be incorporated at this layer. We will talk about this later on. Right now we are talking about pure IP routing of IP packets, and how you can have a virtually connection oriented system on that. We will discuss it later on. So, the point is, I mean, unlike data link layer, if you remember, is just the next hop, just the link which is immediately adjacent. So, that has some advantages in the sense that whatever information you require about it are locally available. Here in routing, the major problem is that we are now talking about routing over multiple networks and towards a very remote system, and the packet might have to take many hops, okay, maybe 10, 20, even 30 hops to reach the end point. Okay. And when you take naturally, say, let us say 20 hops, the area you are sort of serving becomes so large with so many machines connected to it, and how do you keep track, and then naturally with so many machines with so many links, the problem is some of the link may go down, some of the machines may go down, some of the machines may come up, and when I say machines, it may refer to actual either PCs, servers, etc. They may also refer to the network boxes like other routers, alright. Then you calculate the checksum, which is for error connection, as we know, can transmit to the next hop. Okay. Or send an ICMP packet if necessary. ICMP is for Internet Control Message Protocol. So, if the routers may use ICMP packets for sort of talking to each other and sending various messages if necessary, we will see one example at least now and more later.